In this session, we'll try to derive the power and torque equations. We have already derived the equivalent circuit. We have discussed the power flow diagram. So, using using the knowledge of power flow diagram and the knowledge of power equivalent circuit, we'll derive the power and torque equations of the induction motor. This is the equivalent circuit of an induction motor. Here we represent the input voltage. In one phase of the induction motor, R1 is the stator resistance, X1 is the leakage, the inductive reactance associated with the leakage flux on the stator side. X2 is the inductive reactance associated with the leakage flux on the rotor side. R2 is the rotor resistance. S is the slip of the induction motor. RC and XM are the resistance and the reactances of the magnetizing circuit. We now know that in a three-phase induction motor, uh, the input power is given by the equation V in is root 3 Vt or VLIL cos theta 1. This is the input power of the induction motor. We need to find out the values of stator copper losses, the rotor copper losses, and the core losses in the circuit to derive the air gap power and the converter power, and as well as the power that will be available at the output to the load of the induction motor. To derive the stator copper losses, we need to calculate I1 from this equivalent circuit. Looking from this side, let us find out the total equivalent impedance of this uh, we need to find out the equivalent impedance of this total circuit. Equivalent impedance here will simply be R2 by S plus JX2. So we know that R2 by S and JX2 they are in series. They are in parallel with RC, which is also in parallel with J times XM. So R2 by S plus JX2 is in parallel with JXM, which is in parallel with RC, and the resultant will be in series with R1 plus J times X1. So this is the equivalent impedance of this circuit. Now we know simply that I1 will be V phase, that's the applied voltage to this uh, equivalent circuit, V phase at this point, divided by Z equivalent. So once we have calculated the equivalent impedance of the circuit using this simple equation I is equal to V by Z, we can calculate the value of I1, that's the current flowing through this through the stator windings of the induction motor. Now we know our first type of loss in the circuit is the stator copper loss. So stator copper loss per phase stator copper loss will be given by I square R losses. Here I square refers to I1 square, that is the current flowing through the stator winding, into R1, that's the resistance of the stator windings. Now this will be for, for, for one phase. For combining it for all the three phases, the stator copper losses will be thrice I1 square R1. Secondly, uh, now we need to calculate the core losses in the circuit, in this core losses of the induction motor. Uh, Going back to the equivalent circuit diagram, E1 is the voltage available across the core of the available across the core. So the core losses will be given by 3 times E1 square by RC. E1 is the voltage available across the core and RC is the resistance of the core. So 3 V square by R, this is simply the formula. V square by R gives us the losses. So here in three-phase circuit, it will be 3 E1 square by RC. Then the rotor copper losses. Rotor copper losses will be given as uh, I2 square R2. Now I2 square into R2. I2 is the current flowing through the rotors. I2 is the current flowing in the rotor windings. R2 is the resistance of the rotor winding. For a single phase winding, it will be I2 square R2. For a three phase winding, it will be thrice I2 square R2. This will be the fourth element. Before rotor copper losses, we need to calculate the air gap power PAG. PAG is simply nothing but P in minus P SCL minus P core. In the last session, we discussed that the air gap power is the actual power available between the air gap of the stator and the rotor that actually gets fed to the rotor windings. So it will consist of the input power minus the stator copper loss minus the core losses in the induction motor. So our air gap power we have already calculated. We know the input power. We have calculated the stator copper losses. We have calculated the core losses. So air gap power will be given using this equation, or we can alternately we can also find the air gap power using this equation thrice I2 square R2 by S. Now we know that the power available to the rotor is the air gap power. So in terms of the power available to the rotor, also we can calculate it as I2 square multiplied by R2 by S, the resistance of the rotor. That's actually R2 by S here when referred to the rotor, when referred to the stator side. And for a three-phase circuit, it will be thrice. Rotor copper losses will not take the slip into account. It will only be thrice I2 square R2. So rotor copper loss and the air gap power, they are different. Stator copper loss, the slip of the induction motor is very small. It's nearly 0.00, It's uh, the normal operating for a normal operating condition slip is as low as 3%, that's 0.03. So you can imagine that air gap power will be much larger as compared to the rotor copper losses. uh, Following the rotor copper losses, we discussed that uh, there is the power that gets available to the shaft of the uh, induction motor. It is known as the P converted, or so the P converted will now simply be air gap power minus the rotor copper losses. So using this equation and using this equation, once we substitute them, thrice I2 square R2 by S minus thrice I2 square R2. We'll find out the P converted is thrice I2 square uh, R2 1 by S minus 1 1 by S minus 1, or we can say 1 minus S divided by S. So this is the converted power, that's the power available to the shaft of the induction motor. Uh, then we know we also have the friction losses and the miscellaneous losses, the stray losses. We cannot exactly determine the nature and the equation for these three losses: the friction, the windage, and stray losses. So our output power, that's the actual power available to the load, will now be P converted minus P friction plus windage plus stray losses. So taking into account the friction losses, the windage losses, and the miscellaneous losses, subtracting them from the converted power, we'll get the output power. It's not possible for us to get a numerical equation for the friction losses and windage losses or the stray losses. We'll be roughly calculating the values of these losses. Also, P output is can be calculated using the load torque and the speed of the rotor, the mechanical speed of the rotor. So if we know the load torque and the speed of the load, and we have already calculated the converted power, we'll be able to find out the uh, how much is the friction losses, the windage losses, and the stray losses in this induction motor. So these are the power equations of this induction motor. We need to derive the torque equation from the induced torque. P converted is the power that's available to the shaft of the motor. So it will be actually the converted power that will induce, that will provide the necessary torque that gets induced to the rotor. That will cause the rotation of the that will cause the rotation. We have already calculated that P converted is equal to thrice I2 square thrice I2 square R2 1 minus S by S thrice I2 square R2 by S 1 minus S, where thrice I2 square R2 by S can be written as the air gap power that we already know. So P converted is 1 minus S times PAG. The torque induced because of this power will be P converted divided by omega m, where omega m is the mechanical speed of rotation. P converted is the power available to the shaft of the induction motor. We can write this now as 1 minus S PAG divided by 1 minus S omega S, where omega S is the synchronous speed. We already know that omega m or the omega r, that's the speed of rotation. The rotor speed is equal to 1 minus S times the synchronous speed. So this is the final form of the induced torque, uh, that is PAG divided by omega S. So this will be the torque induced in the rotor. So using these equations, we can calculate the different losses in the induction motor, the stator copper losses, the rotor copper losses, the core losses. Uh, we can derive the converted power, we can derive the air gap power, we can derive the uh, output power provided we know that the provided we know the values of friction losses, the windage losses, and the stray losses in the induction machine. We can also calculate the output power from the load torque and speed equations. We have also calculated the actual amount of torque that's induced. We need to keep in mind the load will apply its own torque, that's referred to as the load torque, and the motor will produce its own electromagnetic torque, that's here referred to as the induced torque. So induced torque we have derived as PAG divided by omega s. Under a balanced condition, the load torque and the induced torque, that's the electromagnetic torque produced by the induction motor, they are equal. Uh, we have to further study the torque speed characteristics of the induction motor that we'll be doing in the next session.